Hello all, welcome to this course on time series modeling and forecasting using R. Now again, just to give you a quick overview of where we are standing with respect to the course material as of now. So I think in the last lecture we started with this entire area about diagnostic checking, right? So let's say you create some model, you identify the optimal orders of the model. So let's say ARMA model with orders P and Q, and then in the last lecture we saw that how do you identify the optimal orders based on some probably information criteria. So let's say AIC, SBC, HQIC, etc. And then I think the next step that we covered was model estimation. So once you identify the correct orders, then how do you estimate all the underlying unknown parameters in the model? So let's say if you are taking an ARMA model, then what exactly are the unknown parameters? So let's say the set of all phi coefficients, then the set of all theta coefficients, and at the end of the day you have that sigma square E, which is nothing but the variance of the error term, right. So this is a collection of all the unknown parameters which need to be estimated using either let's say maximum likelihood approach or something like method of moments approach or probably least squares approach, right. And then in the last lecture we talked about model diagnostic checking. So once you are through with let's say fixing the orders and model estimation, then how do you basically ensure that all the model assumptions are met or not, okay. And I think in the last lecture we start somewhere here. So we were discussing how do you basically detect serial correlation, right. Now just to give you a very quick overview of what exactly you mean by serial correlation. So let's say if you have a random graph or let's say a time series process which looks like something like this, right. So here we can see that you have some serial correlation because any two consecutive points, right, are either above the zero line or below the zero line. So let's say if you have a zero line something like that, then let's say if you take any of the chunks, so for example this one or probably that one or the last one, so in each of these individual chunks you can see that all the observations are kind of located at the same side of the zero line. Right. So in a way any two consecutive observations or any two consecutive lags are kind of correlated, and this can be seen throughout the timeline. So again on the x axis you have time. So let's say as you go down the timeline the same identity or the same kind of a categorization can be observed, alright. And I think the last lecture we talked about one particular hypothesis testing procedure called as box and Pierce test, right. And there we talked about the corresponding test statistic, and then based on the test statistic how do you come to a conclusion and so on and so forth. Now just to complete this idea of serial correlation, the first thing we will do in today's lecture is kind of discuss another hypothesis testing procedure which is given by Lung and Box. So again these are two different people who came up with this modified test kind of jointly. So hence the name Lung and Box modified test, okay. Now under here you have this slightly complicated looking test statistic, but nevertheless it's called as QLB. So LB stands for Lung and Box, and then what exactly is this test statistic dependent on? So you have n square and then a particular summation of all the squared estimated correlation terms, right. So these are squared estimated correlation terms because you have rho hat square, right, depending on obviously how many lags you are taking, and then divided by n minus k. So just one point to make here is that if you look at this structure of the test statistic, it is slightly different. It is slightly different from the one we saw in the Box Pierce test, right. So you have a slight modification here, and then hence the name Lung and Box modified test, okay. Now what exactly do you mean by this H that you see in the formula? So H denotes the number of lags being tested. So let's say 10 or 15 or let's say 20. So depending on how many lags or up to what lag you want to test for serial correlation, you can actually fix the value of H here in the formula, and then as usual n denotes the sample size, okay. And once you get hold of any test statistic for that matter, regardless of whatever hypothesis testing procedure you are performing, if the test statistic happens to be bigger than the tabulated chi-square value, then you have to reject the null, right. So this means that if you are rejecting the null, there is some autocorrelation among the residuals, okay, because remember that the null hypothesis is there is no serial autocorrelation or there is no serial correlation among any of the lags, right. And then obviously the alternative hypothesis is that there exists some serial correlation among the lags. Okay. So, if you are not able to kind of reject the null, then we can say that there is no dependency or there is no serial correlation. On the other hand, if you are able to reject the null, then this means that there is some autocorrelation among the residuals among some of the lags, and one possible solution is that the model needs to be rechecked. Now again, what do you mean by that? So again, from the last lecture, if you remember, so the model needs to be rechecked means that probably you may add 1 or 2 lags in the AR component or the MA component of the corresponding, let's say, ARMA model or ARIMA model, etc. Okay. So I think this is broadly speaking how do you detect serial correlation or dependency among certain lags of the residuals. Okay. Now again, before we proceed to the last item in diagnostic checking, so again I will just quickly remind you of the fact that we are doing all these procedures, for example, let's say serial correlation or checking for normality or checking for, let's say, independence, or the last thing we will do is checking for constant variance, right. So all these ideas are implemented on the residuals of the model and not the actual time series process. Okay. So just to make sure that you are clear on this idea here, right. So you fit the model using some technique, then you get hold of the residuals, which is nothing but y minus y hat kind of a situation, and then once you get hold of the corresponding residuals of that model fit, then all these diagnostic checking entities are applied on the residuals of the fit. Okay. Okay, so I think the last thing that we will cover is how do you detect for changing variance. So changing variance is again a problem, as discussed even earlier in some of the earlier lectures. And by the way, this is a very time series technical term for changing variance, which is called as heteroscedastic in nature or heteroscedasticity. Okay. Now again, if you have a constant variance, then the term is homoscedastic. Okay. So for example, it's asking here, right. So heteroscedasticity implies changing variance. So what will be the term for constant variance? So the term for constant variance is nothing but homoscedastic. So we will say that a process is homoscedastic in nature, or there exists some homoscedasticity if the variance is kind of constant over the entire time span. Okay. Now again, before we proceed with any testing of hypothesis kind of a situation or something like that, I will again quickly remind you of certain situations where such a thing can happen. Okay. Now again, just to quickly remind all of you that again detecting heteroscedasticity for the residuals only or residuals again, right. So again here we are not concerned about the changing variance which is seen in the actual time series process, right. But let us say you fit the process using some model, then you get hold of the residuals, and then all these diagnostic checking have to be applied on the residual data. Okay, now let us say for some reason the residuals are behaving something like this. So here clearly we are seeing a changing variance pattern, right, because initially the variance is small in this region, and then as you go down the timeline the variance is kind of increasing. So here you see a fanning out kind of a pattern, right. And exactly opposite to this can also be observed, let us say something like this, that initially you have quite a lot of variance, but then as you go down the timeline the variance is kind of reducing. Okay. Probably something like that. Okay. So even though initially you have large variance, but then as you go down the line the variance is decreasing. So this is more like funneling in, right. So fanning out and then funneling in kind of a effect. Okay. Or for that matter there could be some other very complex kind of a pattern where you see some changing variance happening in, let us say, localized neighborhoods. So what do you mean by localized neighborhoods? So let us say initially the variance kind of oscillates in this manner, and then suddenly there is an increase in variance, and then probably again the variance is kind of again in a very tight band, something like this. Okay. So rather than kind of variance being increased or decreased like in overall nature, so you see some localized behaviors of kind of fixed patterns among the changing variance. Okay. Alright, but now nevertheless if the variance is changing, it becomes difficult to kind of monitor or kind of model the data using a single model, and then we have seen that before. Okay. So hence this is again a problem, it requires some diagnostic checking. Okay. So now again what do you exactly mean by this in terms of, let us say, if you want to use a technical term for this, so let us say it occurs if the errors are having a non-constant variance structure, or in other words variance of the error terms. So variance of Et happens to be sigma square t, and then clearly the sigma square t, since it depends on t there, it must be changing as t changes. Okay, or otherwise if you simply write down, let's say, variance of Et to be some constant, so let's say sigma square, then here since sigma square does not depend on the t, we'll say that variance is kind of constant. All right. So hopefully the idea of changing variance is clear, and then the idea as to why it is a problem is clear. Okay. Now how do you deal with it, or for that matter how do you detect it? So the first very important idea is to create some ACF and PACF plots, right. So again, ACF is autocorrelation function, and then PACF is partial autocorrelation function, and I think a couple of classes back we talked about in detail about how do you plot these two, and then how do you read from these two plots and so on. But here a very important kind of a comment is that rather than creating ACF and PACF plots for the actual data, right, we have to create ACF and PACF plots of the squared residuals and then not the actual residuals. Okay. So we have to create ACF and PACF plots for the squared residuals. Now of course one can actually analyze ACF and PACF plots of the actual residuals also, but creating ACF and PACF plots of the squared residuals is much more informative, and we will see exactly why. Okay. So again, just to summarize, rather than creating ACF and PACF plots of ET, we have to actually go for creating ACF and PACF plots for something like ET square. And why exactly? Because one very important assumption in our case is that expected value of all the errors is nothing but 0, right. So this is an assumption. So expectation of all the error terms is 0. And since the expectation is 0, if you talk about variance of ET, because here remember that we are more concerned about changing variance and not changing mean, right, because mean is 0, but we are more focusing on how the variance structure changes. Okay. So if the mean is 0, variance becomes nothing but expectation of ET square. This is a very standard formula, right, because variance of any random variable is nothing but expected value of x square minus E of x whole square. Right, but then in this case E of x is simply 0. So variance of ET boils down to expectation of ET square in a way, right. So won't it make more sense to kind of focus more on the squared residual term rather than the actual residual term, because variance is directly linked to the square of the corresponding residuals. Okay. So again, just to reiterate the same idea, so you have a small comment here that since all the errors have a 0 mean, the variance is defined by the expectation of the second moment, right. So second moment is nothing but ET square and the expectation of that, which are nothing but the squared residuals. Okay. Thus, if the variance of errors are indeed constant, then what should you observe? So the ACF and PACF plots of the squared residuals should be within those 95% bounds or 95% limits. Okay. So in a way, if indeed the variance happens to be constant, then you should probably see something like this. So let's say these are the 95% bands. So probably apart from the first correlation, basically all the further correlation should be within the band. So this, and then again this should be true for both ACF as well as PACF, by the way. So again in the PACF we have the same structure, right. So you have these 95% limits, and then again if all the correlations apart from let's say the first one are in between the bounds, we will say that they are not significant basically, isn't it. So again if you remember from one of the earlier lectures that if all the spikes apart from the first one are in between the bounds, we kind of conclude that all the correlations at those particular lags are not significant. Okay. And hence there is no question of basically changing variance, because you have a stationary kind of a residual series, isn't it. Because if you are observing something like this in both the ACF and the PACF plots, right, for the squared residuals, then we can actually assume that the squared residuals have a stationary structure, and whenever any model or any process has a stationary structure, the variance has to be constant. Okay. So what do you again mean by stationary structure? So probably if you are observing something like this in both the plots, and then you create a simple plot of let's say t versus something like ET square, then it should kind of resemble a completely random and a stationary structure where the mean is constant, the variance is constant, etc. Okay. So in a way ACF and PACF plot of the squared residual is a very good kind of a visual check to kind of ensure that the variance is indeed constant or is it changing. Okay. But of course we will not stop just by looking at some visual checks. We of course have some formal hypothesis testing procedures also. Okay. But then just before covering those, we'll cover a small section about what could be the outcomes of changing variance, or what could be the certain outcomes of heteroscedastic nature. Okay. So, these are all the outcomes. So, let us say parameter estimates would be unbiased, but not efficient. Okay. So, if the variance is changing, even if the parameter estimates are unbiased, but they may not be that much efficient. Okay. And then second one is one has to use generalized least squares or weighted least squares for estimation. So, rather than using something like ordinary least squares or OLS, which kind of breaks down here because variance is changing, right. So, you have to adopt some other technique. So, let us say generalized least squares or weighted least squares. Okay. So, probably we will talk about this idea in slightly later lecture, but probably just to give you a very short overview of, let us say, how would you apply WLS. So, WLS stands for weighted least squares. Okay. Now, again the idea is, if you can just visualize in your heads that if the variance structure is kind of changing, for example like that, right. So, you have to control the changing variance somehow, right. So, one very important way here is that, let us say you put some larger weights for these observations, because here the variance is small, right. So, let us say you put some large weight to all of these residuals, large weights, and then wherever you see larger variance you put small weights. So, for example, here you put small weights. Okay. So, again if you kind of combine this idea, then at the end of the day you're kind of balancing the entire variance structure. So, if you are putting smaller weights to larger variance and larger weights to smaller variance, then aren't you balancing out the entire variance structure? Okay. So, this is an important idea or important solution when it comes to conquering or kind of controlling for that changing variance idea. And now the third one is that the estimate of the variance is also a biased estimator. So, unlike if the process is stationary where the sample variance is unbiased for the population variance, but then here in this case if you estimate the variance structure, that will not be an unbiased estimator, but it will be a biased estimator, which is a problem again, right. So, thus classical testing procedures are kind of invalid, because you do not have unbiasedness, you do not have efficiency and stuff like that. Okay. So, these are some kind of important outcomes if the variance structure is indeed changing. Okay. So, I think now we will discuss two important hypothesis testing procedures when it comes to kind of controlling or kind of detecting changing variance. Alright. Now, the first one is called as White's general test. So, again this is given by a person called as White, of course, and again let us say what exactly is the null hypothesis. So, in both the testing procedures, in fact the null hypothesis is kind of similar. So, let us say H naught is, if you talk about variance of the residuals, this is nothing but the expectation of Et square given all the data up to, let us say, t minus 1, right, which is nothing but sigma square E, right, which is a constant, because sigma square E does not depend on t. Okay. So, in other words H naught is nothing but that the variance is constant basically. Okay. So, in other words this means that the null hypothesis is variance is constant. So, variance is not changing. Okay. Now, again here if you clearly see that we do not have any expectation of Et term, because expectation of Et is 0 as per the assumption, right. So, variance kind of depends only on expectation of Et square term. Alright. Okay. So, let us say after estimating all the parameters, so let us say you are working with some ARMA model or AR model, ARIMA model, MA model, whatever, but then let us say you come up with all the estimated parameters, you plug in all the estimated parameters in the model, and then you can actually obtain the residual and its square, isn't it. So, let us say if the actual time series process is Yt, then you apply some estimation technique, get hold of Yt hat, alright, and then these are nothing but my Et hat values, which are residual values. Okay. So, from these Et hat values, if you simply square these, you can actually also get Et hat square values. Alright. So, after estimating the parameters, we get hold of Et hat and Et hat squared values. Now, here under the White's general test, the idea is kind of not that difficult. So, you construct this following artificial regression. Okay. So, here this is a slightly complicated model, maybe in the first glance, but we will try to explain that what is going on here. Okay. So, how exactly firstly is this artificial regression, because you are kind of regressing some variable on few of the other variables, okay, and hence it is a regression. And then again this equation on the right hand side contains a bunch of unknown parameters. Okay. So, again just for a second, if you kind of look at this model, this should resemble a kind of a linear regression, or for that matter some non-linear regression kind of a structure. Okay. Now, what exactly goes inside this regression is that now we are focusing more on ET squared values, right. So, we are kind of assuming that the ET square values are the dependent variables, and then here what exactly are the independent variables in this regression are nothing but the historical values of the time series itself. So, let us say yt minus 1, yt minus 2 along with let us say their squared term. So, yt minus 1 square, yt minus 2 square, right, along with any of the interactions. So, by the way, these kind of terms where you have a product of two lags is called as an interaction term. So, yt minus 1 into yt minus 2, right. Now, this is one important point here is that why do you want to include all the squared terms here? Because we are focusing more on the ET square, right, and then ET square should come or should contain some notion of squared time series processes also. So, yt square or yt minus 1 square, etc. Okay. So, in order to construct this artificial regression, we are kind of assuming that ET square is a dependent variable, which is kind of dependent on all these other values. So, yt minus 1, yt minus 2, yt minus 1 square, or for that matter all the interaction terms yt minus 1 into yt minus 2, etc. And then lastly you have this error term as you have in any other regression model, and then you have this intercept. So, alpha naught. Okay. And again here, so let us say alpha 1, alpha 2, gamma 1, gamma 2, delta 1 are all the unknown parameters. All right. Okay. So, what next? So, once you create this artificial regression, then obviously if the variance is kind of constant, right, or under the homoscedastic nature, or homoscedastic case implies that all these coefficients should be equal to 0, isn't it? So, again you can go back a slide and then from this regression you can actually sense. So, if all these coefficients are 0, by the way, alpha 1, alpha 2, gamma 1, gamma 2, delta 1, then my ET square is kind of independent of time, right. So, my ET square term is independent of time and then hence stationary basically. Okay. So, under a homoscedastic case, all these intermediate coefficients should be equal to 0, which sort of boils down to this particular test statistic. Okay. So, you basically look at n into r square of ET hat square, okay, n into r square of ET hat square. Now, by the way, what exactly is r square? So, this r square is nothing but the coefficient of determination of the artificial regression that you have created. Okay. So, coefficient of determination of the artificial regression that you have created, and then this should actually follow a chi-square distribution here. Okay. So, this is the test statistic, and again once you get hold of a test statistic, we kind of test the hypothesis in a usual manner. So, now again one more point here is that where m is the number of variables in the artificial regression. Okay. So, how many variables are there in the artificial regression is nothing but given by m except the constant term, alright, except the constant term. Now, again the same kind of a conclusion. So, you look at this test statistic, right. So, either if the value of this test statistic exceeds the tabulated chi-square m value, then you reject the null, or the other way to conclude is based on the p value basically. Okay. So, this is pretty much the Weit's general test, and then on the other hand you have another test which is called as Bruch-Pagan. Okay. So, again the idea is kind of similar. So, again under the null hypothesis you have the same kind of a structure that variance should be constant. Okay. Now, here the idea of how do you construct that intermediate regression is slightly different. So, here we are not basing, if you look at this closely, we are not basing our ET square hat values on any of the squared terms. So, can you see that? So, in the Weit's test we are kind of basing those terms on the yt minus 1 square or yt minus 2 square terms or yt minus 1 into yt minus 2 terms, right. But in this regression you do not see any such terms. Okay. So, this is more like a simplistic looking regression term. So, alpha naught plus alpha 1 yt minus 1 plus alpha 2 yt minus 2 all the way up to alpha m yt minus m plus the error term. Okay. And again the same kind of a story, that test if all the slope coefficients are 0 or not. So, again if all these alpha 1, alpha 2 up to alpha m happen to be 0, then my ET square hat term would be kind of constant, right, and then the squared residual would resemble a stationary kind of a series. Okay. So, under both these tests the idea is kind of similar, right. So, essentially what you are testing for is that whether my intermediate slope coefficients, so alphas or gammas or deltas, are equal to 0 or not, basically. Okay. Yeah, so this is again under the homoscedastic case, that if all the coefficients happen to be 0, then you have a constant variance case. Okay, then you have a constant variance case. And so again under the Bruce-Pagan test, you have a similar kind of a story, that this is the test statistic under Bruce-Pagan, where again m is the number of variables in the artificial regression except the constant term, and again the same conclusion can be drawn. So if you look at the p-value, and if the p-value happens to be less than alpha, the corresponding alpha, then you reject the null, or otherwise you fail to reject the null. Okay. Alright, so what exactly could be consequences of heteroscedasticity, right? So once you encounter changing variance, or once you encounter heteroscedasticity in the time series process or the underlying residuals, what could be some of the consequences of that? Okay. So if there is heteroscedasticity, the error variance is not constant and is changing over time, right? So I think we discussed this a lot of time in this lecture, that the error variance is not constant and is changing over time. Thus, we need to model the volatility of the underlying process. So in time series literature, you have a thing called as how volatile is the time series process, or is there volatility in the model, or is there volatility in the underlying time series process, and one requires some sophisticated time series models for that, which are called as, let's say, ARCH or GARCH. So ARCH is what? So ARCH is autoregressive conditional heteroscedasticity, or GARCH is generalized autoregressive heteroscedasticity. Alright. Now again, I am missing conditional here. So both are conditional, by the way. So ARCH is simply autoregressive CH, and then GARCH is generalized autoregressive CH. Okay. And probably we will discuss both these models, ARCH and GARCH, in very much detail in slightly later stage of the course, right, where we will talk more about how do you model volatility, right, or rather than modeling the actual mean or something like that. Okay. So more on these models slightly later. Okay. So now in the next 2-3 minutes, we will quickly discuss a practical approach or a practical example, and then kind of combining all that we have discussed. Okay. So again, probably you must have seen this data sometime back in one of the earlier lectures. So what exactly is this? So this is closing stock price of Google for 1000 consecutive trading days between, let's say, 25th February 2013 and 13th February 2017. So roughly 4 years of data. Okay. And this is exactly how the time series of the Google stock price looks like. So you have some trend, right? So you have some sharp behaviors. For example, here you can see that the price suddenly jumped, right, in this region. Okay. So variance might not be again constant. So we have to delve deep into this example. Now again, all these kind of plots and all these pictures can be easily obtained in R. So probably we will discuss in depth in the next lecture, which is a practical one. Okay. Okay. So by the way, so here in the top you can see a simple plot of the residuals. Okay. So residuals using a naive method. So this is exactly how the residuals behave. So here again you can see that you see a sharp change or sharp upward behavior or a sharp jump in the residuals. But again, if you ignore this, apart from that sharp jump, all the residuals are kind of resembling a stationary series. Okay. And again, if you draw the ACF plot of the residuals, then all the correlations are inside the band. So it means that the correlations are not significant. Now again, if you talk about normality, so here you see that you have an outlier here, right? But apart from this outlier, otherwise you have a symmetric kind of a curve, isn't it? Okay. So if you ignore this outlier, and probably this outlier is again clearly because of this jump that you see here. Alright. So if you ignore that outlier completely, then otherwise you have a kind of a normal looking structure. So essentially we don't have any major problems when it comes to, let's say, behavior of the residuals or the ACF plot or normality, etc. Okay. Yeah. So again, this is a normal QQ plot. So normal QQ plot, now again you can see the outlier here, but again if you ignore that, then almost all the points kind of fall along a straight line, which kind of ensures normality in a sense. Alright. And then lastly, if you talk about Box and Pierce test or Box and Lung test, so in both these tests you can see that the p value is bigger than alpha, so 0.3886 and then 0.3551. So since the p value is bigger than alpha in both the cases, then we fail to reject the null, right? So we failed to reject the null, which means that there is no serial autocorrelation whatsoever. Okay. So what could be a conclusion? So conclusion is, apart from that jump, so you do have some outliers. So how do you deal with outliers is one situation. But let's say if you simply ignore the outlier, because here if you ignore the outlier, you are only ignoring just one observation pretty much, right? So let's say the best thing to do here could be ignoring the outlier and then refitting the model. Okay. So if you ignore the outlier, other than the outlier, you don't have any major problem. So both the serial correlation checks are kind of matching. And again, if you go back just a slide, then here you can see that normality apart from this outlier is kind of met, right? And here let's say behavior of residuals apart from this sharp jump is kind of looking stationary. There is no serial correlation coming from the ACF plot, and from the histogram itself it looks normal. Okay. So it kind of checks all the boxes as we want. All right. So I think the next lecture will do some practical things in R, and then just to sort of combine this entire idea about diagnostic checking in general. All right. Thank you.